This is the first of two videos that will cover everything you need to know about proton NMR spectroscopy, from figuring out how many proton or hydrogen environments there are in a molecule, making sense of chemical shift, interpreting data sheets, to understanding the vital information that splitting patterns give us. There is a method to interpreting a proton NMR spectrum. Here we have the spectrum for ethanol, and what we're looking for every time are four distinct things. Firstly, we're looking for the number of peaks or signals that we have. For ethanol, clearly we can see that we've got 1, 2, 3. Each of these is a distinct signal. We're looking for the position of each peak. And by position, chemical shift. So we can read the number directly off the horizontal scale at the bottom of the spectrum. The third thing we're interested in is the intensity of each peak, because the intensity tells us the ratio of protons or hydrogen atoms in each chemical environment. At A level, this information is written on the spectrum. Makes it very nice and simple. And finally, we're interested in the appearance of each of our peaks or signals. And by appearance, this is what we're looking at, the fine detail. Are our peaks single, or does it look like they've been split in some way? And this last thing, appearance, is what I'm going to start by covering in the second of the videos on NMR spectroscopy. Let's start with number. The number of peaks on a spectrum simply tells us how many proton environments are present, i.e., how many different types of hydrogen atom we have in our molecule. My first example is chloromethane. In chloromethane, we've got 3 protons, 3 hydrogen atoms. They are all bonded to the same carbon atom, and that carbon atom is bonded to chlorine. Now, these protons are said to be equivalent. As far as they're concerned, they're all identical. They're all in exactly the same chemical environment. So on the spectrum, we would expect to see just a single peak. We have one proton environment. However, over here on the right, I've got my molecule ethyl ethanoate. In ethyl ethanoate, there are 3 different proton environments. These 3 protons are equivalent. They're bonded to a carbon that is adjacent to a carbonyl group. The word adjacent is very important in NMR spectroscopy. In fact, I'd go as far as saying that no A-level exam question answer is complete without the use of the word adjacent. So we would have a peak for those 3 protons. These 2 protons are bonded to a carbon, and that carbon is directly bonded to oxygen with a single bond. Those 2 protons are in a separate, a different chemical environment, so they would have their peak. And then finally, these protons out here on the end, they're part of a methyl group, but this methyl group isn't adjacent to a carbonyl group, it's just part of a chain, so this third chemical environment would give us yet another peak. 3 peaks, 3 chemical environments. Propanone, over here on the left, is an example of a symmetrical molecule. I have got 2 methyl groups arranged around a carbonyl group. We've got 6 protons, and they are all equivalent. They're all in the same chemical environment as far as they're concerned. They are each bonded to a carbon, and that carbon is bonded to a carbonyl group, whether we're looking from the left or the right-hand side of the molecule. And then finally, we're going to have a look here at methyl benzene. Here we have got, well, we need to be a little bit careful here. We've certainly got one proton environment up here. These three protons are part of a methyl group, and that methyl group is bonded directly to a benzene ring. So we're going to have a signal for those three. How about the 5 protons that are directly bonded to carbon atoms that are part of the ring system? Well, technically, we've got 3 different proton environments. Because of the methyl group, these 2 protons are going to be in a very slightly different chemical environment. These 2 protons or this proton at the bottom. However, their peaks, their signals are going to be so close together that to all intents and purposes, we're going to see one peak. It's going to be a slightly messy peak, and it might look more like that. You're going to have to be a little bit careful about looking at these sorts of proton environment, and I would advise you to go back to your syllabus to check whether you would be looking at 1 proton environment, because all protons are bonded to the ring, or 3 different proton environments there. We need to assign each peak on our spectrum a chemical shift value, and this is telling us the position of the peak. Vice versa, the position of the peak gives us a huge amount of information about the chemical environment of that particular proton, and it's part of the detective evidence we need to help us piece together the structure of unknown molecules. Now, your data sheet is likely to come in one of 2 types. OCR are quite keen on giving you a data sheet that looks like so. AQA prefer this type of data sheet. They're both giving us the same amount of information, the same type of information. It's really important that you become familiar with the data sheet that you will have in your exam. So for the rest of this video, I strongly advise you dig out your data sheet and use it alongside the video. Interpreting the data sheet takes a lot of practice. There's a bit of an art to it, and it's really easy to make mistakes. The first thing I want to point out is this here. That H stands for a proton in that environment. It's not telling me how many protons I have in that environment. So for example, if I had a methyl group, I've got 3 protons, but they're all equivalent. Each of those protons is bonded to a carbon that's part of a chain, for example. So we would expect our peak to be in that range. And if I were looking at this particular data sheet, RCH3 is there. R just stands for any alkyl group. So methyl, ethyl, propyl, butyl, it's part of a carbon-hydrogen chain. In the table data sheet, you'll notice that if I were to, let's get rid of that, replace that hydrogen, say, with another methyl group, then these 2 protons are part of CH2, R2, and we've got a slightly different range where we'd expect to see our peak. On the data sheet that looks like this, it's all lumped together as one type of proton environment. So practice makes perfect here. So let's assign some chemical shift values to the protons of the molecules we've already looked at. Our first one was chloromethane. I've got 3 protons, each bonded to a carbon, and that carbon is bonded to a chlorine. So if I were to go back to my data sheet, I am looking for a proton bonded to a carbon, carbon bonded to a chlorine, or adjacent to the chlorine. So I'm looking for a peak that would be in the range of around about 3.1 to 4.2. So back on my spectrum, 3.1, let's stick it about there. And there are 3 protons in that environment, so it would have 3H written above it. Our second molecule, ethyl ethanoate, we decided that there were 3 proton environments in this particular molecule. So the first one, I have got 3 protons, in this environment. This carbon is adjacent to a carbonyl group. So the type of proton I'm looking for is a proton bonded to a carbon adjacent to a carbonyl group. So that's that one there and that one there. And we would expect to see a peak in reality at 2.1. So if I were to go back, we'd see a peak at 2.1 and it would have 3H written above it. We've got 3 protons in that environment. Our second environment, I've got 2 protons bonded to a carbon, and that carbon is bonded directly to oxygen. So I'm looking for a proton bonded to a carbon, bonded to oxygen. So this is the type of proton I'm looking for. And we would expect to see a peak in the range 1.1 to 4.2. If we look it up particularly, we know that it actually turns out to be at 4.2, so we'll put it in there. And there are 2 protons in that environment, so there'd be 2H written above that peak. And then finally, we've got our 3 protons on the end here, bonded to a carbon that's just part of a chain, nothing exciting going on there. So we've already seen that that would be the kind of range of chemical shift we'd expect to see a peak in, and it turns out that it's at 1.3 in reality, so we would see a peak at 1.3, and again it would have 3H written above it because there are 3 protons in that particular environment. Moving on to propanone. In propanone, we've got 6 protons, but they are all equivalent. They're all bonded to a carbon that's adjacent to a carbonyl group. So we have just seen that this is the type of proton that we're interested in. And in propanone, we find that there is a single peak at 2.2. So it would be 2.2, and it would have 6H written above it. Look, an H just about, 6H written above it because there are 6 protons in that particular environment. And finally, methyl benzene. We identified 2 proton environments. We've got these 3 equivalent protons, and they are bonded to a carbon, and that carbon is bonded to a benzene ring. And if we go back to our data sheet, well, we are looking at this type of proton here. So a proton bonded to a carbon that's bonded to, not actually part of, a benzene ring. Interestingly, on the data table, they don't include benzyl or aryl types of protons or NMR. So we would expect a peak at 2.3. Where are we? 2.3. So we would see a peak about there with 3 protons on that. And keeping things simple, we are going to treat the 5 protons that are directly bonded to carbon atoms that are part of the benzene ring as equivalent. So again, looking back, I'm looking for protons at a higher chemical shift, round about, what does that look like? Maybe 6.2 to 8. And we find in practice that these protons give us a chemical shift at 7. I'm going to make it slightly messy to indicate that actually these protons are not exactly in the same chemical environment, and we'd have 5H written above that peak there. As you study your data sheet, hopefully you'll start to notice some patterns emerge. Firstly, that the higher the chemical shift value, the closer the proton is to an electron withdrawing group. So that's an electronegative atom: oxygen, nitrogen, chlorine, bromine. So we see a pattern. We see an increasing chemical shift value for the protons. The ones nearest bromine, nearest our electron withdrawing group, these protons are being deshielded If that means nothing to you, I suggest very strongly you go back and look at the first video on NMR. But we see a chemical shift of around 3.4 for these two protons, 1.9 and 1.0. Similarly, if I switch my bromine for a fluorine, the chemical shift jumps from 3.4 for those protons to 4.5. Fluorine is much more strongly electron withdrawing. Those protons are more strongly de-shielded. We can also use the chemical shift data to determine whether a proton is part of a methyl group, i.e. CH3. So this is methyl, and we'd expect to see a chemical shift of around 2.7 parts per million. It's a part of a CH2 group, so that would be methylene. We'd expect a chemical shift of around 3.5 for those particular protons, or whether it's a single proton bonded to a carbon. So in that case, methane, chemical shift of 4.3. And if our proton is close to more than one functional group or electron withdrawing group, the effect on the chemical shift is going to be cumulative. So here we've got two protons bonded to a carbon that is adjacent to an oxygen. Chemical shift here is 3.4 parts per million. But here my two protons are sandwiched between a carbonyl group, oxygen's electron withdrawing, and this oxygen. And the cumulative effect pushes up my chemical shift to round about 4.6 parts per million. The next thing we need to understand is why the chemical shift of protons that are bonded to carbon atoms that are either part of a benzene ring or a carbonyl group, such as an aldehyde or even an alkene, why the chemical shift of these protons is so high. What's going on here? These three types of molecule of functional group all have delocalized pi electrons, either as part of a ring system, as in benzene, or as part of a double bond. And when we place these molecules in the external magnetic field, which is what is happening when we're doing NMR spectroscopy, the delocalized pi electrons begin to circulate. So we have our pi electrons circulating in the ring system, in the double bonds, whether it's a carbon-carbon double bond or a carbon-oxygen double bond. And circulating electrons induce a small local magnetic field which increases the magnitude of the external field experienced by the protons. So these protons are essentially de-shielded. They experience a greater magnetic field, which means that their chemical shift is going to be higher. So we see that for protons directly bonded to a benzene ring, a chemical shift of 7.4 parts per million is common. In an alkene, we're looking at a chemical shift of around 5.3. And with the carbonyl group, particularly for an aldehyde, these protons here, the chemical shift is going to be way up at around 9.6, which makes them nice and easy to spot on a spectrum. The final thing I want to talk about is the chemical shift of protons that are directly bonded to oxygen or nitrogen, OH groups, NH groups. As we can see, we would expect the peak, well, to turn up absolutely anywhere. There doesn't really seem to be a lot of rhyme or reason to it. In addition to the peak for an OH or NH proton, so we're talking about these sorts of protons here, being absolutely anywhere, the peak is often really, really small and quite broad. And the reason is because these molecules are capable of hydrogen bonding, either between themselves or between themselves and a polar solvent. And this affects the electron density around the proton. Not only have we got electron density being withdrawn because it's being pulled towards the oxygen or the nitrogen atom they're actually bonded to, It's also being pulled away as a result of the hydrogen bond. And hydrogen bonds are transient. They're coming and going. They're being formed. They're being broken. So we see the chemical shift for these particular protons being variable. Hence the peak turning up anywhere and it being broad, not nice and sharp. So how do we definitively figure out whether we've got an OH or an NH present? So how do we definitively find out whether we've got one of these protons? Well, the answer is to run two NMR spectra, one with our molecule and its normal sample and solvent and just what we'd expect. We've seen this spectrum already for ethanol. Secondly, we shake our sample with D2O, where the deuterium replaces the proton in the OH or the NH group, which means that the peak for this proton disappears. So this peak is not there. If we compare the spectra for the deuterated ethanol with our original sample, we don't see the peak. That is our definitive evidence. So we've covered the number of peaks, we have covered the position, and the third thing on our list was the intensity. The intensity is determined by the total area under the peak, not the height, common misconception. And the intensity tells us the relative number of protons in each chemical environment. Now, on a professional NMR spectrum, this information is summarized in the form of an integration curve, which is worked out by the computer and printed on our spectrum. As I said, at A level, the relative number of protons in each environment is simply written next to the peak. The second of these videos that covers everything you need to know about proton NMR spectroscopy is going to look at the appearance of our peaks. We're going to explain why some peaks, like this one here, looks like a normal peak, but other peaks look like they have been split. And then we're going to look at lots of examples, followed by some exam question practice. If this has been useful, then please hit the like button and subscribe. It makes a huge difference to a small channel like us. And if you head over to the Crunch Chemistry website, there's a link in the blurb below. You'll find notes, exam question practice and answers, and lots of really useful stuff to help you get through this A-level. I look forward to seeing you next time.